This is the lecture video for day 4, so hopefully you're watching this before class on Monday because we're going to discuss it then. Now, moving forward, we're going to be using a few more equations than we've used so far, and I'm going to ask you to occasionally do something like calculate a standard deviation, which, as we'll see, is something that's kind of tedious to do by hand. And the reason that we're going to actually be calculating a few things like this by hand is not because I want you to be able to have this skill of calculating standard deviation by hand, but instead to give us some sort of intuition for how standard deviation works and why it behaves the way that it does. So for the most part, especially for large data sets, we're going to ask a computer, as in R, to calculate things like standard deviation and future things we'll talk about as well. We're going to ask the computer to calculate those things for us. That said, we're almost always going to at least once calculate them by hand, just because it's important to be thinking about what goes into this equation. So in this class in general, whenever I ask you to do something like perform some calculation, the emphasis should be less on following the right steps and hitting the right numbers on a calculator, which I'm sure everyone can do. The focus should instead be on why is this behaving the way that it does. Okay. Now, last class we talked about distributions and various properties that they have relating to their shape, their center, and their spread. This class we're going to be taking a more numerical approach towards calculating these things like center and spread. So we talked about this last time, but we can find the median of a distribution by just picking out whatever its middle term is. Right? And we also talked last time about a formula for calculating the mean, or the average, and that is just, we're going to add up all the entries and divide by however many entries there are. So the summation notation for that is going to be the capital sigma of y divided by n. In other words, add up all of the y's and divide by how many y's there are. We're also going to introduce a convention where we call this mean y bar. So when we have the line above the y, the way that we pronounce that would be y bar. Last time we also talked about this idea of measuring the spread of a distribution. We want to give ourselves a sense of scale. We want to know what the dimensions are for how wide the distribution is. And like with center, we're going to have two different numerical ways of representing this idea of a spread. And the first one is related to the median. It's called the interquartile range. And we're going to calculate this by subtracting the third quartile from the first quartile. Okay, so more about that in a second, but just so that we can complete our picture here, we're also going to be looking for an analogous version of this that is more associated to the mean, and this is called the standard deviation. Both of these numbers, the interquartile range and the standard deviation, which we're going to write S, both of these numbers are telling us very similar things. They're giving us a sense of scale of how spread out the data set is. Okay, so more about both of them. First, interquartile range. So if we have a data set, like let's say an assortment of shoe lengths, sure. We want to find, or if our goal is to find the interquartile range, or even a sort of a bigger project to find, to make the box plot for this, then we're first going to need to be able to find what's called the 5-number summary. We're looking for the min, the max, the median, and Q1 and Q3. Okay, so first, the median, because we have a total of 11 terms here. The median is the middle term. In this case, it's going to be the sixth term, which is just 10. So this is the median. The min is going to be the smallest term, and the max is the biggest. No surprises there. Now, Q1, which is the first quartile, is going to be the median of the smaller half of the distribution. So the median splits our distribution into two pieces. We're going to take, to find Q1, Q1 is the median of the first half. Q2 is the median Q3 is the median of the second half. So to find Q1, we're going to take these 6 numbers and we're going to say, all right, Q1 is whatever is right here, which is, well, the number between 9.5 and 9.5 is 9.5. This is Q1. Similarly, to find Q3, we're looking for the number that goes right here. The number between 10 and 10.5 is 10.25. So whenever you're taking the median or Q1 or Q3 and the number that you want, or the middle number doesn't really make sense because there's an even number of things and there are 2 middle numbers, we're just going to average those 2 middle numbers. So this is Q3. Right. So collectively, these numbers, 9, 9.5, 10, 10.25, and 11, give us what's called the 5-number summary. This is what we need in order to make a box plot. So first off, one thing that we could do, since we started off by just saying, what is the interquartile range? Well, the interquartile range, IQR, is Q3 minus Q1, or in this case, 10.25 minus 9.5, which is 0.75. Cool. So this is some number that gives us some sort of sense of scale of how spread out this whole distribution is. Turning this into a box plot is fairly straightforward. We're going to take these 5 numbers and record, since I'm doing a horizontal box plot, record vertical lines where each of these values are. So 9, 9.5, 10, 10.25, and 11. And we're going to close off this first part with a box. And the stuff outside of the box is represented with whiskers, which look like that. Okay, so we have a box plot. By itself, this doesn't necessarily tell us a ton, but these box plots are really useful, especially when comparing data amongst different distributions. Okay. This is mostly how you make a box plot. There is one exception that I've been glossing over, that now that we have this interquartile range language, we can go back and address. So what we haven't talked about yet are outliers. Outliers are going to be any points that are notably far away from the rest of the distribution. And if I were to give you an example of a histogram where you've got a point that's way off to the side, it's pretty easy to look at it and be like, okay, yeah, that one is an outlier. We want to make this numerical. We want to have some actual definition for what it means to be an outlier. And we're going to do that based off of being a certain distance away from the middle relative to the interquartile range. In other words, using the interquartile range, we're going to set up some region that is these points in this region are not outliers region. Okay, so what we're going to do is we're going to take this interquartile range value, which is the distance between Q1 and Q3, And we're going to scale it up by a little bit. So we're going to take this distance, we're going to scale it up to something a little bit bigger, and we're going to take that unit of measurement and we're going to say, all right, the upper limit is that distance above Q3 and that distance below Q1. Okay, let's apply that to our example. We said that the interquartile range is 0.75, so 1.5 times the interquartile range should be 1.125. And so this is the amount above Q3 or below Q1 we can look. So I'm going to put this in quotes, the not an outlier region is going to be the region that is Q1 minus 1.125, which I believe is 8.375, and Q3 plus 1.125, which should be 11.375. So in other words, we're saying that if a point in this data set lies in this interval, then it's not an outlier. Okay, so as it turns out, none of our points here were outliers, so our box plot is correct. However, if we had a slightly different data set, so we're going to change our data set, we're going to say that, hey, we are no longer, this last point is no longer 11, we're going to say instead it's 12. Okay, we now have a new data set, a new collection of shoe lengths. We want to go through and make let's make another box plots down here. Okay, so in order to do so, we need to find the 5-number summary. Thankfully, the 5-number summary, at least for the first 4 numbers, is going to be the exact same thing. The median, 10, is still right in the middle. These numbers are still the same. Our max is now 12, so we're going to address that. All right. So it's tempting to say that, all right, our new box plot looks like this, where over here now all of a sudden we have 12. All right, it's tempting to say that, but the box and whisker plots are supposed to acknowledge outliers separately. If we went through this whole process with our new distribution, we would actually end up getting the exact same region, because this depends on medians, and medians aren't swayed by one value being notably higher. Okay, so because of that, the not an outlier region is the same for our new data set. But now all of a sudden this point is an outlier. So we're going to make a note of that. And we're going to treat it differently when it comes to making our box plot. So when we draw these vertical lines, we want what I sort of think of as an adjusted 5-number summary, rather than the min, Q1, median, Q3, and max. The mins and maxes are instead mins other than outliers and maxes other than outliers. In other words, we want our upper limit to not depend on 12, but instead depend on the biggest non-outlier number. So we're going to adjust this a little bit. We're going to erase this much, and we're going to say that, hey, the whisker should only go up to 10.5, but we still want to acknowledge that 12 was a number that was a part of this. So we're going to draw an X or a star or something similar at 12 to acknowledge that, hey, there is a point there, but it's so far different than everything else, we're sort of going to treat it as a separate entity. And this is a thing that we're going to do a lot. Whenever we have an outlier, whenever we have some component of our distribution that is so different than the rest of the distribution that we think that maybe something weird is going on, we're not going to get rid of it. It's a perfectly valid data point, but we are going to acknowledge it. We're going to point out that it's there and maybe treat it a little bit differently in some of the methods that we're going to be using in the future. Okay, but for now, this is how we're going to define an outlier. It's anything not in this particular not an outlier range. And if we were to make a box plot, we're going to treat it separately. We're going to mark it with a star, and we're going to use the whiskers only going out to non-outlier mins and maxes. One question you might have at this point is, why 1.5? Why is it 1.5 times the interquartile range that gives us our outlier versus non-outlier region? And that's a great question that is somewhat arbitrary. So John Turkey was the mathematician who came up with this idea of a box plot, and at some point he was asked, all right, why is it 1.5 and not something else? And the response was, well, 1 didn't seem like enough, and 2 was too much. So, and I don't know if that story is apocryphal or not, but I just love that it reflects the idea that a lot of the cutoffs that will come up, that we'll see in statistics in general, a lot of these cutoffs are kind of arbitrary. Like, what's the threshold at which we think one thing or the other? What's the threshold that makes something an outlier or not? Is kind of subjective, and there are conventions that have been adopted, but for the most part, they're kind of arbitrary cutoffs. So that's just something to keep in mind, is to take these conventions with a grain of salt. Okay, now hopefully we can see that the interquartile range and the median are very related concepts. We're going to be talking about the standard deviation, which is similarly related to the mean. We wouldn't ever really use mean and interquartile range in the same sentence, just like we wouldn't use median and standard deviation in the same sentence. We want to use median and IQR and mean and standard deviation together. Okay, so the standard deviation, which we're going to denote S, has a slightly more complicated formula. So the standard deviation is defined to be this thing. And we're going to walk through what exactly this big messy formula really means. Okay, so what we're going to do is, if we have some data set, so I'm going to be drawing just a few points on a line like this, completely arbitrary points. Say we had, say these 1, 2, 3, 7 points was our data set, and maybe we calculated the mean, and we said that the average was right around 6. So we're going to say that the y bar is 6. Okay, so we want to get a sense of how spread out the data is. We want some number that gives us a sense of like how big this error bar, this region should be. And the way that we're going to do that is we're going to take each of the points and we're going to say, all right, how far away is this point away from the mean? So for the first point, it's going to be 6 minus 1, that's that distance. This point is, or I suppose 1 minus 6, but we're going to be squaring it, so the negative sign doesn't really matter. Maybe this is 2 minus 6, 3 minus 6, maybe this one's 5 minus 6. We're going to be adding up something related to these distances. So for each point, how far away from the average are you? And then we're going to square those numbers and then add them up. So this portion is saying add up the squares of the distances to the mean. The distances of each point to the mean. Okay. And then we're going to take that, divide it by n minus 1, and then take the square roots. Right? So a lot of different steps there, but this number is going to give us a sense of what the scale for this distribution is. So we went through this process, and let's start doing it. I'm not going to do it all live, but say this first number was 1, or the second number is 2, then s is going to be the square root of, well, 6 minus 1 squared plus 6 minus 2 squared, etc., all divided by 1, 2, 3, 4, 5, 6, 7. So 7 minus 1 is 6. So then this is going to give us the standard deviation, which in this case, because I'm not working with actual numbers, I'm just going to approximate. I think this would be about, let's say, 2.5. So in other words, that is about this distance. And it gives us a sense of scale as to how distributed our data set is. Okay. The most common question people have about where this formula comes from is, why is it n minus 1 and not n? And the answer is a little bit more subtle than it really needs to be, but the hand-wavy explanation is that, well, n minus 1 has to do with how many degrees of freedom we have. So if we were to try to talk about the standard deviation with only 1 point, just as a concept, that just doesn't make any sense, right? How spread out is the data set if our entire data set is maybe just a single point here? It just, like, as a concept, it just doesn't make sense. If we added a second point, it starts to make a little bit of sense, right? Whatever's in the middle, then we can talk about the separation of each of the points to the middle, and so forth. And if we added more points, so a third, a fourth, a fifth point, then the complexity is sort of starting to go up. And so the reason that we're going to end up dividing by n minus 1 and not n is because the complexity doesn't ever really start until you're at the n equals 2 case. And then from then on, it makes more sense. So for n equals 1, nothing really makes sense. N equals 2, that's sort of our base case. So we're going to be dividing by 1 in that case. Okay. If that didn't make a ton of sense, don't worry too much. Typically, we're going to be working with larger data sets where n is a big number, and then the difference between n minus 1 and n really doesn't actually matter all that much. This is just one of those technicalities that, we want to address. Really not that important right now why we're using n minus 1 and not n. Cool. I keep saying things like the standard deviation gives us a sense of scale of the spread of a distribution. What I mean by that is we can actually use this number that we've just calculated to standardize distributions. Okay, what we have here are two different distributions that look very similar. It's almost like they came from the same image or something, but they are on very different scales. So the first one ranges from 0 to 70, the second one ranges from 12 to 19. So if we actually had these numbers, we could go through and calculate the mean of each and the standard deviation of each. Just pretending that I've done that, we're going to say that the mean of the first one is about 35. So on the left, we're going to write y bar equals 35. Whereas on the right, the mean looks to be about 15.5. Right. Also, if we had these numbers, we could find the standard deviations either by going through by hand and using the formula that we just talked about, which takes each point, calculates how far away from the mean we are, squares it, adds them all up, divides by n-1, and then square roots. Or we could just ask R to do it for us. We're pretending that we've done one of those two things, and that on the left, the standard deviation is about 20, and on the right, the standard deviation is 2. Okay, so we're going to use this information to standardize our sense of scale. Let's take a point that is way above the mean. Let's take the point 65 on the left distribution, and let's take a very similar point of 18.5 on the right distribution. All right. On the left, this 65 is a full 30 above the mean, whereas 18.5 is only 3 above the mean. So does that mean that 65, that this point is like way further away from the middle in our left distribution than 18 is on the right? Well, no, because the scale of these things are different, right? And so our measure of that scale is the standard deviation. So we're going to use this to standardize measurements. Because one thing that we're going to do a lot coming up is ask questions like, right, how far away from the mean is a certain point? And we don't really mean, all right, 60 minus 35. What we mean is, how many standard deviations away from the mean we are. Okay, the way that we're going to do this is called taking the z-score. So z-score is a number of standard deviations away from the average. So this is going to be calculated by taking your points, subtracting the mean, the average, and dividing by the standard deviation. Okay, let's see it in action. For their left example, we want to know how many standard deviations away from the mean is a particular point. Well, on the left, we're going to get that 65, which is the point in question, minus the mean, divided by the standard deviation, ends up being 1.5. If the standard deviation is a unit of measurement, this 0.65 is 1.5 of those above the mean. Similarly, on the right, we can do pretty much the exact same thing, where 18.5 minus 15.5 over 2 is also 1.5 standard deviations. So on the right, that is also 1.5 of these units. It's worth pointing out that these things can be negative. The z-score of, let's say, of the point 15, so now I'm interested in this point. If I want to know the z-score of that thing, well, we're going to follow that same formula. It's 15 minus 35. Notice in the past I've said that it often sort of doesn't matter. Well, it doesn't matter what order you go in if you're squaring it. Here we're not squaring it. So 15 minus 35 over 20 should be equal to -1. So a negative z-score means that your value, the point in question, is less than the mean. So we often say that it's to the left of the mean, whereas values that are bigger than it are to the right of the mean. In the next rounds of videos, we're going to start talking about normal distributions, which are distributions that follow a very specific shape. Now, with these distributions, once you know the mean and the standard deviation, that's actually going to let us be able to figure out a lot about how much of the distribution is between certain values. And in that sense, we're going to keep using the standard deviation distance, or the value of the standard deviation, as a unit of measurement. So we're going to keep using terms like, oh, this point is 3 standard deviations above the mean, which is something that's in this picture way off to the right. But we'll be addressing that next time.